Alright, so in this example we have a simple mixing device which basically consists of a plunger which is rotating and moving up and down. And we're asked to find the maximum magnitude of acceleration of point A on the outer perimeter of this mixing device if theta dot is equal to omega is a constant and n, this quantity that's inside the vertical position of this, is also a constant. Now, I think the key thing here is really in identifying which coordinate set we want to use. And the thing that we're going to do to help ourselves out with that is realize that there's already a r variable in this problem. And so given that piece of information, it makes sense that we're going to want to use a polar description of motion. So in this regard, I'm going to probably make an E sub r unit vector, something like this, that's pointing radially outward. And in this case, you can think of this as being at the origin down here. I'm going to go ahead and align a k-axis in the vertical direction to be aligned with the z-axis here. And you can imagine at this instant that E sub theta is going to be pointing out of the page at us because that'll be the direction of increasing theta, which is the direction of omega. So if we have that, we can then say that the acceleration vector, in this case in cylindrical coordinates, is going to be given by quantity r double dot minus r times theta dot squared in the E sub r direction, plus quantity 2 r dot theta dot plus r times theta double dot in the E sub theta, plus in this case z double dot in the k. Now in this particular problem, we know a little bit more information than what I've included here immediately. First of all, we know that the radius of this, that is the distance between points A and O as shown in the drawing, is fixed. And that means that both r double dot and r dot will both be 0. In addition, we're told in the problem statement that theta dot is equal to omega is equal to a constant. And that of course means that theta double dot is also going to be 0. So if we simplify our acceleration here a little bit to start, we're going to have the acceleration is equal to minus r times theta dot, which is omega, quantity squared in the E sub r, plus z double dot in the k. Now of course the challenge at this point is to realize that we still haven't solved for z double dot, and so that's exactly what I want to do next. So we note in the problem statement that we're given z is equal to some z naught times the sine of 2 pi times n times t. In this case, we know that n is a constant. So if I want to find the first time derivative of that, I'm going to have that z dot is going to equal 2 times pi times n times z naught times the cosine of 2 pi nt. And if I take the time derivative of that, I'll get that z double dot is going to equal now 4 pi squared n squared z naught times the sine of 2 pi nt, and in this case with a minus sign out front of it from the derivative of the cosine. If I substitute this back into my expression for acceleration, what I'm going to have is that the acceleration of point A is equal to minus r omega squared in the E sub r minus 4 pi squared n squared z naught times the sine of 2 times pi times n times t. Now if we read the problem statement carefully, we're asked to find the magnitude of acceleration, and in particular maximum magnitude of acceleration. And so the thing here to think about is, well, the only thing that's going to vary with time is the term that I'm going to highlight here, the sine 2 pi nt term. And we know that at the extremum, this is going to be exactly plus or minus 1. And so if I, for example, choose a case where this is going to be, say, minus 1, you could choose plus 1 and do something similar, then what you're going to have is that the A max, if you would, here, and in particular, I want to find the maximum magnitude, so I'm going to find the maximum magnitude is going to be, in this case, the square root of the maximum of the first component, which is going to be r squared omega to the fourth, and I'm going to add to that the square of the second component at its maximum, which would be, in this case, 4 pi squared n squared z naught all squared. And so this answer right here will be the maximum value that we can obtain for the acceleration in this problem. I think that about wraps this up. Best of luck as you work to reproduce this.